So good Thursday afternoon, everyone. Welcome to Mathematics for Construction, lecture 19. Oh, we did lecture 18. We started talking about probability properly because I don't really like how the textbook does it. Right? We did some questions here because that's the point of class. I give you some definitions because I find the textbook kind of lacking, especially in this area. It doesn't explain things very well. So today we want to talk about something that is even more confusing. This is probably one of the most confusing things in mathematics. The idea of counting. Okay, apparently humans are not very good at counting. As it turns out, there are many things we cannot count. Okay, so counting is the topic. What you all think counting is not really what counting is in a mathematical sense. Huh? Right? The parent counting or the theory of counting is a subtopic under a branch of mathematics called combinatorics. Combinatorics is one of the oldest branches of sophisticated mathematics, right? The older ones being, number theory and algebra and graph theory and those kind of things. So it's a fancy name, but it's the idea of enumerating all possibilities of a problem. Okay, that's the idea, and it helps in probability. We're just going to do enough of it to help us understand how to solve problems. Okay, so the first thing you normally talk about in counting is and or no, and we did that last week. So if you have somebody ask you, well, if it has, you have 5 colors that you could pick, right? Say red, orange, blue, green, yellow, right? So you have these 5 colors here that you could choose from. And I say, pick 3 colors, right? How many possibilities exist, right? So one choice could be blue, green, yellow. Another choice could be red, orange, blue. Another choice could be yellow, blue, red, right? Any question you might ask yourself, does order matter? So if you pick red, orange, blue, is that different from blue, orange, red? That kind of thing. So does order matter? Because if order matters, then the answer is different, right? So these kinds of problems where you're picking things, you have to come up with a proper vocabulary. You have to agree on a certain terminology before we start talking, because you don't want to get confused, because it is a confusing topic by itself. So so we say a combination is a choice, or what we call a selection. Selection, if I could spell it. Right? So a choice of items or order is not important. That's what we call a selection or a combination, right? And we say a permutation And common synonyms for permutation or arrangement. When you see that word arrangement, it means, you know, the order is important, right? So, you know, I have these 5 colors here. I could choose 3 colors, right? So choice, same thing here, choice. The choice or selection, all these are synonyms. Order is not important. Put this in big. Order is not important. So choice, I could say, well, I want blue, yellow, green. So this is one choice. This is one combination, right? So that's one combination of the 5 colors that we have. Now this combination, there are many permutations or many arrangements of it. I could do blue, yellow, green. That's one arrangement. I could do blue, green, yellow. I could do yellow, blue, green. Could do yellow, green, blue. Could do green, blue, yellow, green, yellow, blue. See? All these are different permutations. All these are different arrangements of one combination, blue, yellow, green. Okay? So this gets the terminology right. What's the difference between a permutation and a combination? A combination or a selection or a choice is just pick 3 of them where the order is not important. But when you, after you pick them, you could rearrange them now, okay, amongst themselves. So I hope this clarifies things. So again, you know, we have 5 colors here. We could represent them as initials, R, O, B, G, Y. A combination is a selection where order is not important. So blue, yellow, green is one combination. Another combination is red, orange, yellow, okay? The order is not important in a combination, but an individual combination can be permuted, can be arranged. So this one combination here, blue, yellow, green, we could have arrangements of that, and we have 6 arrangements here, right? What does the textbook say about permutations and combinations? Page 357, in the probability chapter, right? We have a section called permutations and combinations. So let me just read and see what I have to say. If you have n distinct objects available, we can arrange them in different ways. Each arrangement is called a permutation. So example, if you have the letters X, Y, and Z, you have 6 ways to permute that, right? Each one is a different arrangement. So we represent this terminology here, 3p3. P is the permutation function on your calculator. It takes 2 arguments. The top number is the number of items in total, and the bottom number is how many items from that list you want to permute. And it gives you the number of ways to permute R objects from a list of n objects. We'll see the function just now, okay? So it looks a little scary. NPR, you might see that button on your calculator. There's a formula for it, right? It's n factorial over n minus r factorial. Factorial of a number is just the product of that number and all the numbers less than it up until 1. Okay, it's really defined for integers. Okay, so like 5 factorial is 5 by 4 by 3 by 2 by 1. That function explodes fast. Okay, worse than exponential. Right, it goes even faster than an exponential function. So for very small numbers, factorial gets really big, very, very quick. And it's just a formula, right? NPR is the number of permutations of R distinct objects from a list of n distinct objects. Okay, so it might look like just a formula, but there's a lot of reasoning involved and thinking involved in how you apply this thing, right? They're trying to tell you here that 0 factorial is defined as 1. You could do it in a calculator. Where is this factorial function going? Calculated. Do I have it? Yeah, is this exclamation sign here? So if I try 3 factorial, I'll get 6. If I try 5 factorial, I get 120. Right? That's 5 by 4 by 3 by 2 by 1. So that's the exclamation sign there that you see on your calculator. I might have to change the view to get P and C. I'm not seeing it here. Second function. I'm getting tired of it. God. All right. View programmer. Do I have it? No, I don't. All right. So that was brief. Now to go and get a scientific calculator online. So permutations are arrangements, ordered arrangements. Order is important. Combinations, right, is a list of things where the order is not important. So if you pick a list of objects, when the order is not important, that's what you call a combination. So you have 3 letters X, Y, Z are made without regard to the order, that is called a combination. And there's a similar function NCR, the number of combinations of R distinct objects from a list of N objects. And it's given a slightly similar formula here. N factorial divided by R factorial by N minus R factorial. Again, these things will come to haunt you very, very soon, right? So what is 5 choose 4? 5C4. That's the number of choices of 4 objects from 5 objects. Right? So like if you're playing a game and you need to pick 4 people from 5 people, how many ways you could do that? There's 5 ways to pick 4 people from a list of 5 people, where order is not important. The number is a little bit bigger for a permutation. The number of arrangements of 4 objects from 5 objects. Okay, that is a little bit more. So you see you have the example, calculate number of permutations. There are 5 distinct objects taken 2 at a time. So again, if you have 5 colors, like these colors here, and you have to pick 2 of them, how much permutations you could get, right? So like, I mean, listing them out might help you, but that's not how you answer the question, okay? So if you had to pick 2 colors, I could go red, orange, red, blue, red, green, red, yellow. And it's a permutation. So red, orange, and orange, red is 2 different choices. That's 2 different patterns. Okay. So lots of patterns here like blue, green, green, blue, blue, yellow, yellow, blue, green, yellow, yellow, green. Right. You have to have a real systematic way to list this out. And that's what counting is. Counting means enumerate all the possibilities and put a number by each one. That's really what enumeration is. And we humans are not very good at counting, believe it or not, in a mathematical sense. So here, if you have 5 colors and you want to find two permutation patterns from 5, it's 20 possibilities. Okay. If you have 4 distinct objects and you take it to a time, the number is less, 12. Now this is permutations using the formula, right? You can find similar things for combinations. Calculate number of combinations, 5 distinct objects taken 2 at a time. That's 5 choose 2. Yeah, and you just work it out. It says 10 is less than 20, which was the 5P2. 5C2 is less. Generally, for the same N and R, C gives smaller numbers than P because it have more permutations of something than there are combinations, right? One combination will generate several permutations, so the number of combinations will always be less. Our class has 24 students. 4 can represent the class on an exam board. How many combinations are possible? So like if you have to pick 4 people from a class to represent the class, the order not important, you know, that is not a problem where the order is important. If I pick Bob, Mary, Steve, and Jane, it don't matter the order I pick them, it's the same 4 people that are going to represent the class. So order is not important. So for such a problem, I wouldn't use permutations, I would use combinations. If I have 24 people, how many ways could I choose 4 people from that 24? And when I say choose, obviously I mean order not important. Otherwise I would not have used the word choose. Choose means order not important. It's a choice. Choose or select means order not important. So you see this fantastically large number here. That's how much ways you could pick 4 people from 24 people, where the order is not important, obviously. That's a big number, and nobody gonna sit down and write all possible combinations to count that. You use the theory of counting, combinatorics, right? Combinatorics, which is the science of counting. You're using techniques from this branch of mathematics to enumerate all the possibilities, to count all the possibilities. We're not gonna write them down and write numbers next to them. We wouldn't finish, and we might make errors. Similarly, if you have a team, like say playing cricket, right? You have a 16 set of people in your team, your full team is 16, but you need to pick 11 to go and play a one-day international tomorrow. Which 11 people you're gonna pick out of the 16? How many ways you could pick 11 people out of 16? That number not small, you know. Look at here. Again, order is not important, right? If you pick 11 players, the order of the players is not so important at first. You just want these 11 people. Now the batting order, the order in which the players bat, that is not a combination, that's a permutation. The order is important because you have to decide, okay, who is the opening batsman, who go in second, who go in third. It have some players, they have different strengths, and you want to use those strengths to whatever strategy you have for your batting order. Okay, so your batting order in cricket is a permutation, but the choice of the 11 players to represent the side, that's a combination. Okay, so I hope these analogies making sense to you. So I neaten up the notes a little bit here, make things a little bit nicer, right? Permutation, k distinct objects from a list of n. N is always more than k, right? More than or equal to k. This is formula for permutations, this is formula for combinations, and factorial is that function is defined for an integer. Is the product of all the integers less than that number. For example here, how many ways can a team of 6 players be picked from 10 possible players? So if we're picking 6 from 10, order is not important. All right, think about it. Like it don't matter how you pick them, it's the same team. Okay, it's the same team with the same people. The outcome probably gonna be the same because you have the same list of talent available to you, right? So this is a combination problem. So I could just steal this here. That is ten choose 6. So it's 10 factorial over 6 factorial 10 minus 6. What is this? Or we can simplify this. Well, 10 over 6. This obviously is 4 here. 10 over 6. This upstairs here. You will have the 7 times 8 times 9. That is the 6 factorial canceling with the 10. Right? Because remember, the numbers 1 to 6 from down here will cancel with the numbers 1 to 6 in the numerator. Even 7, 8, 9, 10. And this 4 here is is that. So the 8 will cancel with the 2 and the 4. Three will cancel with the 9. Oops, wrong place. So I get, let me see, 7 by 3, which is 21. 10 by 10, 210. I think that's what I have here, 210. Right? So yeah, calculator makes it faster, of course, right? But there's a combination problem because the order is not important, right? So this is a question that I ask, and you know, once you choose these 6 players, you have 6 of them, right? How many ways you could line up 3 players from the 6? Okay, so you have 6 people, A, B, C, D, E, F. 6 people, and you want to pick 3 of them. How many possible lineups you could have? So you could have A, B, C, you could have B, C, D, you could have D, E, A, you could have D, A, B, right? How many possible lineups it have? But that one, this is our ordered arrangement. This is our permutation. So steal this. N is 6 and K is 3. So we get 6 factorial over 6 minus 3. Six factorial over 2 factorial. This is 6 factorial is 1, 2, 3, 4, 5, 6. If you divide that by 2 factorial, what you will do, you will take out the 2. So I get 3, 4, 5, 6. How I got 2 here? I even 3, sorry. So that will take out the 6 over 3. The 3 factorial will cancel 1, 2, 3, leaving the 4, 5, 6. So this is 120, right? So you see the idea of permutations and combinations in an example like this. I hope this makes sense. So you want to move on to something called a probability distribution, specifically a discrete probability distribution. We talk about a discrete random variable. So let's start off with a scenario, right? If we toss a coin twice, the number of heads obtained could be could be what? How much heads could you get if you throw or you toss a coin twice? We deal in heads and tails, right? What are the possible answers you could get for the number of heads obtained? How many possible answers you could get? I throw a coin twice. Is it possible to get 0 heads? Yeah, you get tails 2 times, right? Is it possible to get 1 head? Yeah, you get a head and a tail, or a tail and a head. Again, you see that there's a permutation there. And then it's possible to get 2 heads. So it's really 3 possibilities that you could get, right? Two R's in occurring. So what's the probabilities that these occur? We could say P, probability you get no heads, is what? Should probably put this in a maths. Probability you get no heads. That's the probability you get a tail, followed by the probability you get a tail. And these events are independent, so you can multiply them. Remember the multiplication law for probabilities. Once they're independent, meaning one doesn't affect the other, then and, which means you get it at the same time, is you multiply the probability. Probability of getting a head is the same as getting a tail on a fair coin. Right? That's the probability of getting no heads. What's the probability of getting 1 head? Well, we could to get 1 head, maybe we could write it like this. We could have this convention here. This is an informal convention where we put PTT. PTT means a tail followed by a tail. We could get here a tail or a head, or probability a head followed by a tail, right? So if you get 1 head, how could you get 1 head when you throw a coin twice? So either you get a tail followed by a head, or maybe you get a head followed by a tail. There's a permutation. We just talk about permutations. Now, each of these probabilities here is a product. So that's the first one is P of T times P of H. The second one is a P of H times a P of T. Right, so 1 head turns out to be 0.5. Probably split this up into 2 dimes. What's the probability you get 2 heads? Well, that's simply the probability of a head followed by a head. These are independent events, so we can multiply them. So we can show the results in a table. That table is called a probability distribution. So we could say number of heads 0, 1, or 2. And the probability of each one. So this is what a probability distribution is. We have some variable. We could think of this as a variable here, number of heads. And the variable has discrete values, 0, 1, 2. And for each value, there's a probability associated with that value. So let's talk about that now. The variable being considered is, I put in quotes, the number of heads obtained in 2 tosses of a fair coin. Right? That's what X is. X is a number, right? It's a variable because it have different values. So you could use a capital letter X to represent that variable. So X is a variable that can have discrete values. So that's why we call it a discrete variable. Okay. So a discrete variable is one which maps a value to a probability. Okay, you can think of it as a function. In fact, it's defined as a function in advanced mathematics, right? So when you have a random situation, when you have an experiment, you can identify a variable X being some discrete value in the experiment, and each value is associated a probability. A discrete random variable, that's what a discrete random variable is, gives rise to a discrete probability distribution, where each possible value of the variable has associated with it one probability, okay? And the probability is distributed. So probabilities can be written P x equals 0. So I convert this to some maths here. So px equals 0 equals 0.25. You could put the other guys here as well. So the probability that the discrete variable x is 0 is 0.25, as shown here. The probability that x has a value of 1 is 0.5, and the probability that x equal to is 0.25. And with this notation, the mathematics becomes a lot more concise, but it still carries a lot of meaning, just as before. It's less talking, right? If the sum of the probabilities is 1, this is where the randomness comes from. If the total probability of these things is 1, if all the probabilities add up to 1, for all the discrete values that the variable could have, is said to be a random variable. So it's a variable because it has values associated with it. Is x, right? We call it x. X can have values. X is what? The number of heads obtained when you throw a coin. So x could have possible values. X could be 0 or 1 or 2. That's what we set up here. So it's a variable, right? Now, the values that x can have are discrete values. So that's why it's called a discrete value. Each value that x has is associated with a property, and the sum of all the probabilities over all the values is 1. So it's called a random variable. So herein lies that definition. What is a discrete random variable? Okay. So it's a mouthload. It's like Teenage Mutant Ninja Turtles, you know. Not only are they turtles, they're ninjas and they're mutants, right? And they're teenagers, right? I have a lot of things going on there, a lot of adjectives, right? Same thing with discrete random variables. It's a variable that is random and discrete. And it gives rise to a distribution, what we call a probability distribution, because each possible value of the variable there is a probability associated with it. So we normally write that sorry, take this. So we don't usually write it probability distribution like how you have this table here up here. We normally do it differently. So I could copy this. We don't use lowercase, we don't use uppercase letters for variables. The lowercase letter is used to represent the value, and the uppercase letter is used to represent the actual variable. So sometimes you would say you could use another letter like A, right? Say A, and probability x equals A. So A has values 0, 1, and 2. What is the probability that x has that value? And you put the probabilities here. Oops. So we normally write that like this here. The sum of all the probabilities of X being A over all the A. We sum it over all the A's, right? We sum it, and our total sum is 1. So we want to talk less and do use more mathematics, okay? So we're not gonna use too much of words. What we plan to use is more like these equation type things, P of X equals A. So that's the idea of a discrete random variable. A variable which has discrete values, and each value is associated with a probability that it could have that value. Right? So it's discrete variable. Every sum of the probabilities is one is called a random, so a discrete random variable. And we show the probability distribution like this. Right? So I hope that makes sense. So when you see things like dv, it means a discrete variable. That's the abbreviation dv, right? X is a discrete variable. The number of 4s obtained when 2 fair dice are thrown. So you know what a die is? That's 6 faces. And we throw in 2 of them. We throw in 2 of them, and they're going to land on some numbers, 2 numbers. Whatever 2 numbers we get, we want to see if we get 2 4s. What's the chances of that happening? Like how much, what was the values X could have? They say show that X is a DRV. So you know it's a DV, a discrete variable, because it has discrete values, but showing it's a random variable means find any probability distribution and show any probabilities add up to 1. Okay, so you have to do the table. So let me go to check the solution. When when 2 fair dice are thrown, number of 4s obtained can be 0, 1, or 2, right? Those are the possible number of 4s that you could get. So let's do some of the things we were doing up here, right? Steal this. Using this notation. So I want to find these things here. Okay. What is the probability that X is 0? Meaning you throw a die, 2 dice, and you get no 4s. You get no 4s, right? What has to happen? What has happened for you to get no 4s? Both die shows a score that's not 4. So we could write it, you know, we could write it P. That means, oops. You didn't get a 4. You didn't get a 4. That's what the bar means, right? Like in vectors, that bar on top of number means not. So we get 2 scores that were not 4s. Now, the score obtained on one die is independent of the score obtained on the other die. The die don't affect each other, right? Throwing them together, one does not affect the other, so they're independent events. So that means the chances of not getting a 4 on one die is the same as the chances I get not getting a 4 on the other die, right? So these probabilities here, because it's an and, we multiply them. So this is P. So probability of not obtaining a 4 squared. Right? Was it probability of not getting a 4? 5, 6, right? The probability of not getting a 4 when you throw a die is 5 or 6, because the probability of getting a 4 is 1 out of 6. So not getting a 4 is 1 minus that, which is 5 over 6. Yikes. A 5 over 6, that is, if you square that, you get 25 over 36. Right? That's probability of x is 0. So is a big probability actually, right? More than half. So more than half your chances that when you throw 2 die, you're gonna get 0 4s. Both of them will not show any 4s. What's the chance of getting 1 4 though? Well, the first die could be a 4, and the second could not be a 4. Or the first die could not be a 4, and the second could be a 4. Right? So what is this first probability here? That's probability of getting a 4 times the probability of not getting a 4. And we add that around. Right? So the first die I got a 4, the second die I didn't get a 4. Or the first die I didn't get a 4, and the second die I got a 4. So these things is lots of fractions. So the probability that you got a 4 is 1 over 6 times 5 over 6. That's the probability you didn't get a 4. Plus the reverse. You didn't get a 4 on the first die, but you got a 4 on the second die. So this is 5 over 36 plus 5 over 36. That's 10 over 36. Right? That's the probability that one of the die has a score of 4. What's the chances that you got 2 4s? Well, that's a real rare one. That's you know, that's like getting snake eyes when you throw 2 dice. 2 1s. It's the same as getting 2 4s. So using the notation we have here is the chances again of 4 followed by a 4. There's a probability of getting a 4 all squared because you're multiplying it by itself. But the probability of getting a 4 is 1/6. That's a real small chance. That's 1 on 36. Okay. Now, where's the summary probabilities? Let's check this out here. So it's summation over all the different A's for probability of X equal A. Or we could use P if you want, just don't use the same letter, right? Small p is all the probabilities, right? But the reason why I don't use P because you already have a big P. So that's why I'm using things like A, right? It don't matter what the letter is. It just means all the different probabilities. What is the sum of all of them at X equals that value? So we will add the different fractions, right? So we come here, we say, okay, we add the 25 over 36 plus the 10 over 36 plus the 1 over 36. And what is that equal to? Well, that's 36 over 36, which is 1. So the summation of the probabilities over all the A's, that the fact that X has that value, right, is the summation over all the possible values of the discrete variable. X is a discrete variable, it has different values. We want to sum all the values of P of X equal that value, right? So it means you're adding up all the probabilities. Is 1. So we could do a table for this here. Right. So 25 on 36, 10 on 36, 1 on 36. So the discrete variable has values 0, 1, and 2. The probabilities associated with each of them is shown here. When we add up all those probabilities over all the different values of A, we want to sum the probability of X equals A. When we do that, we get 1. So this shows that X is a discrete random variable. Okay, that's how you do a question like this here. This is just to build your understanding of what probability distribution is for a discrete random variable. So the normal dice that we see is 6 sided, has 6 faces because it's in the shape of a cube. We have other types of dice. It's just that the more faces they have is the more spherical they tend to become, and then they tend to roll a lot, right? But there is something called a tetrahedral dice. This is a dice with 4 faces in the shape of a tetrahedron. The faces have the scores 1, 2, 3, 4. And if you throw 2 tetrahedral dice and you look at the score, we have different values that could be, okay? Find the probability distribution of that discrete random variable X being the sum of scores obtained when 2 fair tetrahedral dice are thrown. So you throw 2 dice, look at the scores. What is the probability distribution function? What's the table for that? That's what I want you to do right now. You're going to do the problem the way we did the problem before, where you look at X. What is X? What are the possible sums X could have? Those are the values X could take. For example, if I throw the dice, could I get a score at 12? Is it possible to get a score at 12 when you throw 2 tetrahedral dice? How are you going to get 12? The biggest number is 4 and 4. You could only get up to 8. So what's the smallest score you could get? 1 and 1 is 2, right? So the smallest score is 2. And the largest score is 8, 4 and 4. What are the different scores in between, and what are the chances of getting those scores? So for each value, each score X could have, what is the probability that you could get that score? And do up all the probabilities and show that distribution the way we did it before. This will give you practice to help you understand and probability distributions, because we're going to talk about a special probability distribution next. And that distribution kind of ugly because it uses this function here to generate coefficients, right? So it only going to get harder, guys. Trust me, right? Okay, so to help us with the probabilities, we'll do a table to show us the different scores possible based on how when the dice are thrown. Okay, so let me say that here. So we need a table. On 5 columns. So first die score, you could get 1, a 2, a 3, or a 4. Second die score going downwards this way, it could get a 1, a 2, a 3, a 4. So is there a way to merge this boy? All right, so the scores here start from 2, 3, 4, 5, 3, 4, 5, 6. This will be 7, 6, oops, 5, 4, 5, 6, 7, 8. So you add up these scores, right? So how many times you could get a 4? Is you could get a 4, you could get a 1 and a 3, a 2 and a 2, or a 3 and a 1. Okay. So from the table, we can see that X can take the values. What's the smallest value? I'm saying a 2, 3, 4, 5, 6, 7, 8. So 2, 3, 4, 5, 6, 7, 8. These are the values that X could take. So for probability distribution, we could steal this table here and just add columns to it. right? So X could have the value 2, 3, 4, 5, 6, 7, 8. What's the probability that X could have these values here? We use A to be the actual value it could have. And what's the probability that X has that value? So 2, how many times does 2 occur? This is 1 out of how many? There's 1, 2, 3, 4, 4 by 4. There's 16 of them. So 1 out of 60. How many times it could get a 3? I'm seeing two ways it could get a 3. So that's 2 and 16. How about a 4? 3 ways. 5, 1, 2, 3, 4. This is supposed to be a 6, right? So this is a 4 over 16 as well. 6 looks like 3 over 16. 7 is 2. And 8, 1 over 16. Okay. And if you add up these numerators here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, you get 16 over 16. Okay. So X is a discrete random variable, and this is how the distribution looks like. So let me just confirm that, right? Down here, saying, you know, the sum of all the probabilities over the different values that X could have. Let me say that again. The sum of all the probabilities over, that's what is all A here, over all the discrete values that X could have, is adding up all of these things here. Okay, so we have 1 and 16, 2 and 16, 3 and 16, 4 and 16. Let me scroll up. 3 and 16. Right? So if we add up all the numbers, 1, 2, 3, 4. Why does that word equal? Right? 1, 2, 3, 4. And then 3, 2, 1. Right? So 3, 2, 1, 6, 6 and 6, 12, 12 and 4, 16. Right? So X is a discrete random variable. Right? Random because it is some of these probabilities as 1. Discrete because it has these 7 discrete values, right? So this is the solution here. I hope you all understand that. What we talk about here is general discrete random variables, right? General discrete random variables, we have a lot of them. We could examine a situation, identify a discrete random variable, and do the probability distribution for it. Okay, this is general. But there's a specific discrete random variable that you have to learn about with a specific probability distribution, and it's in your textbook. That distribution is called the binomial distribution. Okay, so we're going to read a little bit about what this is here. Binomial distribution deals with two numbers only. Probability that an event can happen and the probability that an event will not happen. So obviously P and Q, when you add it up, you get 1. So if a coin is tossed, P is the probability of coin landing with a head upwards. Q is the opposite, with a tail landing upwards. And P and Q are to be equal to unity. The binomial distribution arises when we do independent trials with the same experiment. So let me say that again. You're doing an experiment several times and you're looking at the output each time. The probability of a success is the same in each trial of the experiment, right? So it's like, think of an experiment like, say you're throwing a die. So you throw a die once, you look at the score. Then you throw it again and you look at the score. Then you throw it again and you look at the score, right? So those are independent trials, one after the other, because they don't affect each other, right? The score you get the second time don't affect the score you get the third time, right? So they're independent. It's successive independent, yes, successive independent trials of the same experiment with the same probability of success. When you do that, the binomial situation arises. If you look at the name comes from the binomial expansion of P plus Q to the power n. The coefficients of the expansion is the coefficients of Pascal's triangle, which is the coefficients NCR, which we had before. Oops, I passed it. NCR. These are the coefficients of Pascal's triangle, which is the binomial expansion. So that's what you're seeing here. So what we're saying here, if P is the probability the event will happen, Q of course is the event that doesn't happen, then the probabilities the event will happen 0, 1, 2, 3, n times in n trials is given by the successive terms of the expansion P plus Q to the n from left to right. That's the concept of the binomial distribution, okay? The function, this function here generates the terms for you. You just have to plug into the formula. So you see, you have some problem here. Determine probability of having at least one girl and one boy in a family of 4 children. Assume equal probability of male and female. And of course, you know, you assume that the gender of the child at any point does not depend on the gender of the child before or after independent trials, right? The trials are independent of each other. So once you have independent trials, meaning the children don't affect each other being born. Like if I have a boy now, that don't mean I'm gonna have a girl after, right? It doesn't depend. It is independent trials, okay? So you're modeling it as 4 trials. So you do 4 experiments. Each experiment is having a child. I mean, that's an expensive and dangerous experiment if you ask me, right? But that's the experiment, having a child, giving birth to another human, right? What is the discrete variable here? They say probability of getting a girl, okay? So that could be a variable. X is the variable, the number of girls. You want to know, well, how much girls could you get in 4 trials? You could get 0, meaning you have all 4 boys. You could get 1, you could get 2, you could get 3, depends. So here the probability of a girl being born is 0.5. And well, the male is equally 0.5. From above, 0, 1, 2, 3, 4 girls in a family of 4 are the possibility. So it's 5 possibilities actually. So what's the chance of no girls? No girls means each time, each of the 4 times you get a 0.5. No girl, no girl, no girl, no girl, 4 times. Because each of the 4 trials are independent, you multiply all the 4 probabilities and you get 0.5 to the power 4. Now, a little more interesting now. What's the probability of getting one girl? Well, maybe I got a girl the first time, followed by 3 boys. But it's possible to get a boy the first time, followed by a girl, followed by 2 boys. Or you could get a boy, a girl, then a boy. Or you could get boy, 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 then a girl. That's 4 possibilities, right? It's 4 permutations in a sense of getting one girl. You could get her the first time, the second time, the third time, or the fourth time. Each time you didn't get a girl 3 times. That's why I have the Q cubed, and then you got the boy 1 time, P. But you have 4 ways you could get that. So that's why I multiply by 4. That's why it's called the binomial theorem. The coefficients of the binomial expansion of the product of brackets gives you the actual probabilities, right? What about you getting 2 girls? How you could get 2 girls? Well, that's out of 4, choose 2. That's 4C2. We did that before up here. If you have 4 girls, and how much ways, sorry, if you have 4 genders, how much ways you could choose 2 girls out of that? That's 4C2. That's 4 over 2 factorial by 2 factorial. Okay. So that'll be 6, as I show you here. And then you multiply, right? Remember, you got 2 girls. So 2 girls, that's P squared. It's 2 successes, and then 2 failures, Q squared. And so on and so forth, right? Notice the total probability is 1, so it's a discrete random variable. The variable, of course, being the number of girls you get out of 4, right? So the probability of having at least 1 girl means you have 1 girl or 2 or 3 or 4. So you can add up these probabilities here. But a better way of doing it is to notice that, well, the total is 1, and having at least 1 means you didn't have 0. So it's just 1 minus that. And you'll get the same answer, 9375, which is what they did here. It's just 1 minus the chance of getting no girl, and this is the chance of at least 1 girl. You see, the probability is very high. Eh? If you have 4 kids, the chances at least one of them is a girl is very high. And we model this as independent successive trials of the same experiment. Each time the probability of a success is the same. That's where the binomial distribution shows up, right? It comes up there. So let's see some other applications here. You have a dice, 6-sided dice. When they say you have a dice and they didn't measure anything else, you assume it's 6-sided, right? And you roll it 9 times. That's 9 different experiments. That is 9 independent trials of the same experiment with the same probability of a success. Now, what you're looking for? You're looking for a 4 or upwards. What's the probability again of 4 or upwards, right? Well, that means you could get a 4, a 5, a 6, right? 4, 5, or 6. So when you throw a die the first time, what's the chance that you're getting a 4 upwards? You have 6 possibilities, and a 4 upwards is 3 out of 6. Right? So that's basically a half. You'll get a 4 and upwards. So that's your probability of a success, right? 1 over 6 is the chance of getting a 4. But then you could get a 5 or a 6 and so on. So having a 4 upwards no times. It means 9 of the times you didn't get a 4. So that's 5 over 6. If you get it once, it means you have a 4, and 8 times you didn't get a 4. But you have 9 ways to get 1, 4. Again, combinations. You have 9 ways of choosing one person from a team of 9 people. You could choose any one of the 9, right? If you had to choose 2 people from a list of 9, that's 9 choose 2. That's what this is here, 36, 9 choose 2. How much ways of choosing 2 ways to get a 4 out of the 9? There are 36 ways of choosing that. That's why these coefficients come into play. Each of these times that you get, each of these 36 times that you get 2 4s, that is why this probability is squared. The other times, the other 7 times, you didn't get a 4, so you multiply these probabilities by themselves 7 times, and so on and so forth. So probability of having a 4 upwards less than 4 times is just the 0, 1, or 2. See, 0, 1, 2, you add them up. This was calculated exactly 3 times, which was this one here. And then we use the others to calculate this one here. That's really it, you know. This industrial inspection is just a way of using the binomial distribution to do quality assurance on the success or failure of something happening in industry. So you say here, if P is the probability a component is defective, one component is defective, right? The binomial distribution arises when you try to look at several components. Okay, so you look at an example. A machine is producing a large number of bolts. They say 95% of them have the right tolerance. So there's 5% defective. So there's a 5% chance that a bolt is defective. That's what this is saying here. So the probability of a success in a sense is 5%, because you're looking for defective bolts. That's when you get defective bolt, that's a success in the experiment. Now they say 7 bolts are drawn. So that means you're doing the experiment 7 times. You're picking up a bolt and you're asking yourself, is this defective or not? Then you pick up an next bolt, is this defective or not? And you do that 7 times. Each time you could get a defective bolt or not. The probability that you get a defective bolt though is 5%, which is very small. So you don't really expect to get that a lot. The binomial distribution arises when we have these 7 independent trials. Each trial is independent, right? When you pick up one bolt, that will affect another bolt. If this bolt defective, that will mean the next one going to be defective. It's independent trials, right? So P is the probability that a bolt is defective. So that's P is 5%, which is 0.05, and Q is the other one, right? So if you draw 7 times, how much defective bolts you could get? You could get none, you could get 1, you could get 2, you could get 3, up until 7. Now, since 5% of the bolts defective, you're probably a small probability that all the bolts going to be defective, all 7 of them. But it's also small that all of them perfect, that you don't have any defective bolts, right? So we have to look at the probability distribution for this problem is 0.95 plus 0.05 to the power 7. This will give you the coefficients. So where's the probability I get no defective bolts? So that means out of the 7 times, every single time you didn't get a defective bolt. That's what our probability is. When you have one way you could get it. What's the chance of getting 1 defective bolt? Well, if out of the 7 times you get 1 bolt, it means 1 bolt defective, that is the probability here. And then the other 6 times you didn't get a defective bolt. So you have to multiply the probabilities because each independent trial is happening here. And then how many ways you could get 1 bolt defective? It could be the first one defective and the other 6 good. It could be the second one defective and the other 6. It could be the third one, the fourth one, right? You get any idea? 7 ways up there are 7 possibilities where 1 bolt out of 7 is defective. And again, we're using N-choose R, NCR. You see it here as well. For 2 defective bolts, this is 7 choose 2. That's 7 factorial over 5 factorial by 2 factorial. So that's 6 by 7 over 2. That's 7 by 3, 21. That's how they get this number here. There are 21 ways to choose 2 defective bolts out of 7. For each of those 21 choices, we got 2 defective bolts and 5 good bolts. That's why that probability is this here. And so on and so forth. It's the same thing over and over again. This is just a histogram. This is just showing you how to plot it. But essentially, it's the same thing over and over. You do the binomial distribution. I will give you a different notation for it because this doesn't have a good notation, I find. This doesn't use the notation that we have for a discrete random variable, which is P of X equals something. This notation is better to do problems with. This notation is very wasteful. There's a lot of writing to answer these questions. There's too much writing. What I will show you all is a better way of representing, but the idea is the same, right? So if you have an experiment with 2 possible outcomes, right? One you could term a success and one a failure. If you perform n independent trials, independent because each one doesn't affect the other one, a binomial situation arises when you consider the number of successes. See this number of successes here, that's what we consider. That's the discrete random variable, the number of successes. For example, one experiment is tossing a coin. But if we do it 6 times, that is 6 independent trials. That is 6 independent experiments. A random variable arises out of that. How many times did you get a head? So if you throw a coin 6 times, how many times it could get a head? Could get 0 time, 1 time, 2 time, 3 time, up until 6. Right? So the X, your random variable, the discrete random variable, the number of heads obtained could be 0, 1, 2, 3, 4, 5, 6. And the probability that X has a certain value is given by the binomial distribution. So we're gonna have a discrete random variable, which is the number of successes, and it's gonna look something like this. It will have different values it could hold, and each value there's a probability. What gives us the probability is the binomial distribution. The binomial distribution is essentially this table here. Each term here is given by a coefficient in the binomial expansion. That's the idea we're heading towards. So we throw a die 10 times. Each one is an experiment. We have 10 experiments and independent because the outcome of one experiment don't affect the outcome of the other, right? And the idea of a success is obtaining a 6. Well, if you throw a die 10 times, how much 6s you could possibly get? You can't get 12 6s. You only throw the die 10 times. You could get 0 up until 10. And each one has a probability associated with it. And the probability associated with it is given by the binomial distribution. That's essentially what it is. So you have this example here. A coin is biased, right? Biased meaning the chance of getting a head is not the same as getting a tail. It says 2/3. And we throw it 4 times. Find probability of obtaining exactly 2 heads, right? So how you could obtain a head? First of all, the chances of getting a head is 2/3. So not getting a head is 1/3, right? It's 1 minus the probability of getting a head. How could you get 2 heads and, well, 2 tails and 2 heads? You didn't get 2 heads first, and then you get 2 heads after. So we had to multiply these 4 probabilities here. The first 2 times we didn't get heads, and then the next 2 times we get heads. So there's the 2 1/3 here being multiplied, and this is the 2 2/3 being multiplied here. Independent experiments That's why we multiply the probabilities, okay? So this is one way of getting two heads only. But how other ways are getting two heads? Like you get a tail, then a head, then a tail, then a head. Or you get a tail, head, tail, head, which is the same thing. Doesn't let me change it. Or you get two heads, then two tails. Right? So this one here should be like that. Right? What if there's the two middle ones we didn't get heads on? The head was either on the outside. What I'm trying to show you here is there are many ways. There are many ways to get two heads when you throw this bias coin 4 times. Well, that's why I have the or dot dot. We're not interested in actually enumerating all the different ways. We know how to do this. The coefficient of the binomial expansion is given by C, which is 4C2, which we did like an hour earlier. Number of ways of choosing 2 positions to get ahead from 4 positions, right? So you have 4 experiments. How much ways that you could have 2 other experiments being successful? Well, it's 2 choose 4 or 4 choose 2, depending on how you say it, right? 4 choose 2 is the proper way to say it. So 4 possibilities and you're picking 2, you're choosing 2 from that. This is not a permutation, huh? Because there's repeats going on here, right? We could think of it as that, right? So therefore, the chance of getting 2 heads is this probability here, but you have 6 ways of getting. That's 4 choose 2. So you have 6 different variations of 2 heads and 2 tails. So you have 6 ways of getting the 1/3 squared by 2/3 squared. So you add them up 6 times and you get 8/27. So this is how the binomial distribution arises. This is just one probability we're trying to find here. The probability of getting 2 heads, right? A similar argument will follow if you wanted to know, okay, you throw the coin 4 times, what's the probability of getting exactly 3 heads now? That's a totally different probability that you have to find. But what you could do is generate a table of all the possible values that the discrete variable could have. How many times did you get a head? 0 time, 1 time, 2 time, 3 time, 4 time. You have 5 different values, and each one you'll get a probability based on NCR or NCK, which is the combinations, number of combinations. From n distinct items, you want K possibilities, right? So next class, we'll make this more concrete and we'll do some problems, but essentially is what they're doing here. You have several trials of the same experiment. The probability of success is the same in each one, and you want to know how much successes you have. What's the chances of getting 1 success, 2 success, 3 success, or maybe even you could say something like, what is the probability of getting at least 3 heads, right? If you try coin 4 times and you ask a question, what is the probability of getting at least 3 heads? It means you get 3 or 4. So there's 2 different probabilities you have to work out. So we'll talk about that next class. But that's essentially the idea behind the binomial distribution. The probabilities are found by powers of P, Q, and this NCK, number combinations of K distinct objects from a total of N objects, which we did earlier, right? So make sure and go through the chapter and see what they're doing here, and I'll give you the notation next week for how we're going to do that binomial distribution, and it will make more sense.